everyone, at the final lecture of this very nice week. I have a few promises to live up to. I said that I would be explaining some parts of the proof of the small world properties in random graphs, and that's what I'll get started with. That'll take a sizable chunk probably of the first hour. And then after the first hour, I would like to explain something. I mean, this whole workshop is called Processes on Random Graphs. So I would like to explain something about processes. So far, we've mainly considered topologies of graphs, either in dynamic settings or in static settings. The kind of problem that I will be looking at are sometimes called information diffusion processes or first passage percolation. So, all right. So a little recap. This is one of the theorems that I presented last Wednesday. And this is the theorem that I'll be considering in terms of the proof. I also discussed some related results for the generalized random graph as well as for preferential attachment models. I'll say a little bit about preferential attachment models in some point of the proof, explaining what the difference is. But this is the theorem that I would like to explain to you where it comes from. So it basically says that if you're in a configuration model where you have finite variance degrees, and assume that the degree distribution converges in distribution, and the first and second moments of the degree distribution converge along, then actually the graph distances are logarithmic with a base nu, and I explained in a bit of detail where the nu comes from, but we'll get back to that as well. So this is the finite variance regime, whereas in the infinite variance regime, what you see is that the graph distances are much smaller. They're even doubly logarithmic. Okay? So how can we understand this? Well, on Wednesday, I started explaining what's happening to the local environment of a uniform vertex. And remember that this hn variable really was the graph distance between a uniform pair of vertices. So if you give me a uniform vertex and I can explore its neighborhood, and I can do the same thing for the other uniform vertex, you know, then at least I'll know a little bit what's going on in terms of the graph exploration. Here you just start with a very simple idea. You start from your uniform vertex, you look at the half edges that come out of it, you pair them uniformly at random, and as I explained on Monday, you can really think of the pairing as being performed in the order that you like. So in this case, it's very convenient to do it in the order of somehow the breadth first order in your exploration process. So basically, you're going to be pairing the half edges of the root vertex, and that will give rise to a new vertex that has another couple of half edges that are as yet unpaired, and then you're going to be pairing them, and so on. Okay? And on Wednesday, I explained that there is something different between the degree of the root vertex, which asymptotically has the limiting degree distribution, and the other vertices, because since we're pairing uniformly at random between the half edges, there is a size biasing coming into the game. So if I look at any of the neighbors of the root, which is actually the degree, its degree would be the degree of the vertex that a half edge is being paired to. And by the pairing, I lose one of its half edges. So if I look at the forward degrees, the distribution is this. And this is nicely behaved. And this is very closely related. It's, in fact, this limiting distribution is the same thing as the size bias distribution -1. Right. Okay, so I gave as an exercise, compute that the expectation of this actually is this new parameter. That's not very difficult. Okay, so we have that nu is the expected value of d times d minus 1 divided by the expected value of d. And that I can think of as being the expected value of the size bias distribution -1 by itself. Because the probability distribution of the size bias distribution -1 is precisely this. You get this extra expectation in the bottom by reweighing the probabilities, and you get this size biasing, which account for this. So you indeed get that this is the relevant parameter. And in this part of the game, we're always assuming that this is larger than 1. Otherwise, there's no giant component. All right. Now this, of course, is a bit intuitive. And the question is how to make this, this more precise. And there is a very nice tool for this, which is sometimes called local weak convergence, sometimes also Benjamini-Schramm convergence. And we will use it in order to describe this fact that all the forward neighbors of the initial starting point are close to IID, and therefore, somehow from a certain moment onwards, it looks like all the offsprings are going to be an IID sequence, and therefore you have a branching process. Okay? And local weak convergence is a way of making that precise for a finite number of stages, for a finite number of generations. All right. So what is local weak convergence? Well, it's a way of describing that a sequence of graphs from a random perspective looks like something in the limit that is either deterministic or random, but it no longer depends on the size of the graph. So precisely like here, what we're trying to prove is that if I look from the perspective of a random individual, its local neighborhood will look like a branching process. And that branching process is, of course, its law is independent of n. So now we've somehow taken a limit. And local weak convergence makes that precise, makes that sharp. Okay? Here are a few references for where you can find proofs. And I will say something about local weak convergence for the configuration model. So first of all, what is local weak convergence? Well, we take the perspective of a random node. Okay? So that actually boils down to, if you take the expectation with respect to a random node, multiplying by 1 over n, which is the probability of taking any of these nodes, and then looking at the neighborhood of width r, of size r, around the chosen vertex, which is here denoted by I. Okay? And then I write this indicator saying that this neighborhood is isomorphic to what you have on the right-hand side. And in this case, it suffices to look at trees, any trees, which are rooted. So Y here denotes the root. So I'm counting the proportion of vertices whose R neighborhood is isomorphic to this rooted tree. That's what I'm counting. And what I would like to show, that's of course in a random graph, this is still a random variable, and what I would like to show is that this object converges as n tends to infinity in probability to a certain object, which describes the limiting graph, the limiting structure, the limiting rooted neighborhood. So in this case, this ought to be the neighborhood in a branching process. But local weak convergence applies much more generally. You could do it for trees, but you can also do it for all sorts of other graphs. It's very nice and powerful methodology. Okay, so how can we do this? Well, let's first try to see why the neighborhood in a configuration model should be related to a branching process in the first place. This branching process in the very first step will still be dependent on n. But that's okay. So what I'll argue is that the local neighborhood of a point, of a vertex, can be coupled to a certain branching process, which depends on n. Let's do this for a random vertex, such that with high probability they are equal. Now, clearly this cannot be done sort of very long, because this branching process could actually survive forever, and then its tree will be infinite. Now, the thing that I'm starting out with is a graph that just has a finite number of vertices. So you're bound to see differences between the two at some point in time. And what the local weak convergence is saying is that this is not coming very early on. Okay? Not in the initial phases. All right. So how could we do this? Well, the whole point is that in the configuration model, what you do is you pair uniformly at random. But after you pair edges, you remove them. And that gives dependence. It's the removal that makes things dependent. So even just starting out, if I have a half edge and I want to pair it, I'm going to be pairing it to something different than itself. So I'm not drawing a uniform half edge out of the whole set of half edges. I'm drawing a uniform half edges out of the collection of half edges that is not the half edge that I'm currently pairing. So it's not quite a uniform half edge, but you know, this half edge is only one out of a whole zoo of half edges of the order n, and therefore it's pretty unlikely that I will actually choose this half edge again. So what instead I could do, and this is precisely what produces the coupling, is that instead of pairing to a uniform half edge that is available, I just draw a uniform half edge every time from the whole collection of half edges. If I do that, then actually the number of forward neighbors of these half edges are going to be IID by default. Because I'm always doing something uniform at random independently of each other. So if I then look at sort of the vertex that I draw, that vertex is actually going to be an IID vertex all the time. So also its forward degree will also be an IID sequence. So this provides a very nice coupling. Now again, of course, if I do my pairing for very, very, very many times, at a certain moment I will see differences. I will actually draw a half edge that I'm not allowed to draw because it's already been used or because, you know, because it's the one that I'm currently at, right? So at a certain moment in time, I might actually create a difference between these two. But the claim is that initially, it's very unlikely that this is going to occur. And even, it's very unlikely to be drawing a half edge that is incident to the tree that I currently have. If that would happen, then I would actually create a cycle in my graph. And that's not good either, because we're trying to prove that the graph, that the local limit is a tree. It's not something that has cycles in it. So there are cycles in the graph, of course, but typically they're pretty far away from any local vertex, any uniform vertex. So that's the coupling. Now so that basically describes what this BP of n is. Okay, so what is it? So the BP of n, it's somehow an n-dependent version of the branching process that I was writing down on the previous slide, which I was intuitively arguing that it would be similar to the graph exploration. What is BP of n? Well, the root has offspring. Well, the number of half edges in a uniform vertex. But that's precisely my random variable dn. Okay? And we know that this dn converges in distribution to some limiting random variable. But of course, it does depend on n. And since with the pairing of the half edges, I'm doing things completely independently, the distribution of all of the forward degrees from now onwards in this approximation will be an IID sequence. So the only thing that I have to compute is the probability that its forward degree is some value. So every other vertex in my branching process will have offspring Well, what is it going to be? Well, the offspring is only the forward half edges, because the half edge that I'm pairing to is eaten up. So we sometimes call these the siblings. So if I draw a vertex and I indicate my half edges as being these small spokes, right? I need to pair two of such spokes to form an edge. Right? And suppose that I've chosen this one, then this one is eaten up in order to sort of create the connection to my previous vertex, and therefore I shouldn't count it because this is not going anywhere else. So I'm only counting these. And these I sometimes call the siblings. So these are the siblings of a half edge drawn uniformly at random. Now, the number of siblings of a vertex V is the same thing as the degree of V minus 1. Okay? And also, because I'm drawing a half edge uniformly at random, the probability that I will choose a certain vertex will be precisely the degree divided by the total degree. So, the probability that I draw vertex V, I don't draw my vertices uniformly at random, I draw my half edges uniformly at random. So if my vertex has a humongous degree, I'm much more likely to choose it. So that's just going to be proportional to its degree divided by the sum of the degrees. And that's the same thing as d of v divided by ln. So there's the size biasing. And that actually means that every other vertex has an offspring that is the size bias distribution of d minus 1. The one that is the one that I'm removing here. So the forward degree is only the ones that are going outwards. And I draw this vertex with a probability that's proportional to its number of half edges. Okay? So now I have a branching process that depends on n. The root distribution is slightly different from the distribution at any other vertex. But of course, that doesn't really matter for many properties. And what we see is that the offspring distribution in this branching process is precisely this, the n-dependent size bias degree distribution minus 1. Now, under the assumptions that I was stating, we know that this one actually converges in distribution to this limiting value. And we also know that the mean of this object actually converges to the mean of that. And that statement, in fact, implies that also this one is converging in distribution to the size bias distribution minus 1. Why? Well, this is precisely the probability distribution of dn star minus 1. It's precisely what it is. In fact, this is ln, and this is the number of vertices of degree k plus 1. And if you're assuming that if I divide this through by n, it converges to that, and dividing this through by n, it will converge to that, that's both weak convergence and convergence of the first moment, you actually get that this probability distribution converges to that probability distribution. Now, I've written here in probability, think of the setting where the degrees are IID. Then indeed this converges in probability. In fact, it even converges almost surely. Okay? Now, this means that I have a branching process. It has an n-dependent structure because the root distribution and the distribution of every other vertex depends on n, but they both converge in distribution. And this is an integer random variable, this is an integer random variable, this is an integer random variable, and that is an integer random variable. And we know that if you have convergence in distribution of an integer random variable, then actually also the total variation distance will converge to 0. That actually means that I can couple them in such a way that this one and that one are going to be equal with high probability as n tends to infinity, actually with probability converging to 1. And also these laws will be equal with probability converging to 1. So that actually shows that if I look at the branching process of size n, and then the first r generations of this, which is going to be a finite number, will also converge to this, the first r generations of this limiting branching process. And now we're almost done, because now I've argued it for the branching process, but I haven't quite yet argued why the branching process is, with high probability, a very good approximation of this n-dependent branching processes with high probability, a good approximation to the local neighborhoods. Now that you can do by coupling the two on the same probability space, the branching process that depends on n, and the graph exploration, where we say, you know, every time we just draw a half edge uniformly at random. Now, in some cases, I might be drawing something that I'm not allowed to draw. Then I'm just going to throw it away, and for my graph, I will actually do the right experiment. Okay? Now, since I don't have very many half edges that are being used in these first R generations in the first place, even here, the probability of actually making a mistake is of the order 1 over n for any finite number of generations. Okay? So that couples the graph neighborhood with this n-dependent branching process in such a way that they're the same up to the first R generations with probability of the order 1 minus 1 over n. And there you go. That's produced this coupling, and that actually produces the fact that this convergence holds. So that's local weak convergence for the configuration model. Filling in all the details is slightly more cumbersome, but not very difficult. Basically, these two ingredients are the natural sort of path you would choose. Okay. Now, what do we get out of local weak convergence? I keep on saying that it's a very useful thing, but what does it give us? Well, it's certainly not telling you everything about the graph because it's something local. It's not something global. For example, you cannot deduce what the size of the maximum component is out of this, because the size of the maximum component is clearly a global quantity. What you can show is that from local weak convergence, you get a one-sided bound on Cmax. Somehow Cmax can never be larger than, Cmax over n can never be larger than the proportion of vertices that will survive up to time r for every r. Now, because of local weak convergence, that actually converges, that probability. In fact, it will converge to the survival probability of this limiting branching process. And that actually turns out to be the size of the giant component. Now, if you want to prove that the giant component really has that order of magnitude, what you need to show is that most vertices that survive, so they survive up to time r, that they're actually going to be connected to one another. Now, that's a different story. And you really have to go beyond the local neighborhoods in order to prove this. Okay? Now, there's lots of things that actually immediately converge when you have local weak convergence. For example, for those of you who know some statistical physics, if you look at the log of the partition function of the Ising model scaled by the graph size, this will converge immediately to the similar object defined on the limiting space. It turns out that the page rank distribution also converges. And you have to work a bit harder because this is not exactly a continuous functional, but it turns out that under some stronger restrictions on the degree distribution for the configuration model, also the densest subgraph converges. Okay? Now clearly, because of the definition, the proportion of neighborhoods of a specific shape for the configuration model of a certain tree, where the neighborhood is a certain tree, converges also in probability. So that's what local weak convergence gives. Now, as I said, for many global parameters, it doesn't work. But still, you can use it as a starting point. So for example, if I would want to investigate the graph distance between two vertices, what I could do is I take these two uniform vertices, I grow their R neighborhoods for some R pretty large, and if we're in the giant component, and these R neighborhoods are really described by a branching process, then at the end of the game, I will see lots of vertices on the boundary. And because I have lots of vertices on the boundary, now I've reduced my problem from seeing few vertices, close to the vertices that I found, to a huge number of vertices. And that is actually very convenient. Okay? So, in a certain sense, you could say that local weak convergence gives a good starting point for an analysis, for example, for graph distances. So, how can we do that? Well, if we know that the tree locally grows like a branching process, then it's actually worthwhile investigating how many vertices there are at a given distance. So we've coupled things to a branching process, so this number is just the same thing as the total number of individuals in a certain generation of this branching process. Okay? Now forget about the fact that we're dealing with a random graph and just think about a branching process by itself. And then we know that we have these two different settings. If the expectation of d squared is finite, then the branching process that I get here will have finite mean. That's this size biasing. A finite mean of the, a finite variance of the degree distribution will turn into a finite mean of the branching process. Okay? If I have a branching process with a finite mean, I actually know, well, you need one condition more, an x log x condition, but let's forget about that. We know that the generation sizes actually grow exponentially in K. Okay? So this is the mean offspring of my branching process, which is larger than 1. I raise that to the power minus k. That's exponentially small. If I multiply that by z of k, what I will get is a martingale in k, which is non-negative, and therefore by the martingale convergence theorem, it will actually converge to a limit. Now, under this x log x condition, you can show that on the event of survival, the limit really is strictly positive. And it's also finite. Okay? So that tells me that certainly initially, my neighborhoods will grow exponentially. Now, that, of course, is already going towards the direction of showing that graph distances grow logarithmically. If I can reach points, an exponential number of points in k in a given distance, then my graph distances should be the log of the size of the graph. Okay, so this is going in this direction. And again, here we were assuming that the second moment is finite. Now, there's a little bit more about this that you could say. And that is that there's some law of large numbers effect kicking in this branching process. In fact, if you were to know your branching process up to a given distance, r, then actually this limiting variable here doesn't change much anymore after that. And the reason is that, you know, if r is very large, I'm going to have an exponential number of vertices in the top layer. That's pretty large. And therefore, the number of individuals coming out is IID. So a law of large numbers effect is going to set in. And you know that actually in the next layer, you're going to have roughly nu times the number of individuals in my current layer. Law of large numbers. So in a certain sense, after this generation R that I'm thinking about, which is going to be extremely large, the branching process has decided how large this variable is going to be. Okay? Now suppose I would want to know that I would want to use that for the graph process. Well, you know, this coupling of the branching process to the graph exploration process is fairly nice. In fact, you'll be allowed to use it for a much longer time period than just a finite number of vertices. It turns out that you can do it all the way up to square root of the size of the graph. Now, that's something like a birthday problem, right? So that basically means that if I explore the graph up to a size which is of the order square root of n, I'm very likely not to have created any back edges or any problems in my coupling. So what you can then do is do this from the two vertices that we have, u1 and u2. And you basically grow these until they have size square root of n. Actually, you would need it to be slightly smaller than this, but let's just ignore that. Now, if you know that these grow like nu to the power k for a distance k, you actually also know that this corresponds to a generation which is roughly, well, the log of this divided by the log of nu. And that's actually going equal to 1/2 log n divided by log nu. Or, in other words, log nu of n. So that's 1/2 the graph distance that we've seen in the main theorem. Okay? So if I do this as well from here, I can basically go up to the same generation for my tree. And again, I can do this coupling up to size 1/2 log nu of n. And then I'm going to have roughly square root of n vertices on the boundary. And here I will also have roughly square root of n vertices on the boundary. It's not very difficult to show that then actually you're going to create a clash between them with reasonable probability in a finite number of steps. So this is very suggestive, and it's suggestive to say that this is roughly then the sum of these two plus something which is tight because of the finite number of steps. And that's precisely the result that I was talking about. So here, for our 80 degrees, having at most parallel tails, the fluctuations are bounded. So this says that if I look at the graph distances, I subtract from this number, I get something which is a tight random variable. Okay? So this was the argument, or a sketch of the argument. Of course, making this precise requires a bit more. It's a lot of concentration results and so on, and very fine and detailed coupling. This is basically the philosophy of the proof. Now, the proof changes considerably in the case where tau is in between 2 and 3. Because of the size biasing, if tau is in between 2 and 3, this random variable will have a finite mean. But the size bias distribution will not. So here we're talking about an infinite mean branching process. And actually, if you assume that your degree distribution has a nice parallel tail, then there are some results. For example, there's a beautiful paper by Davies from 1978. Laurie Davies. Later he turned into a statistician. That will show that your generation sizes actually grow doubly exponentially. So finite mean, exponential growth of neighborhoods, infinite mean, sufficiently thick tails, doubly exponential growth. If we then again do this analysis, basically going to size square root of n, of course, the computation of which generation that is changes dramatically. But you can still do this coupling up to size square root of n, roughly. So what does this turn into? Let's do that in a different color. So this is nu is finite. Tau in between 2 and 3. Well, double exponential growth, that actually means that I'm going to need log n divided by the absolute value of log tau minus 2 generations in order for this to grow so quickly that on the boundary you have of the order square root of n. And in fact, because this grows so quickly, just a few steps earlier, I'm going to have a very small power of n. And in fact, for the branching process, if I just do this a few generations longer, I'm going to have many more than n, which of course in my graph I cannot have. So this growth is enormously quickly. Somehow what this says, this statement about the log growing exponentially, it basically says that for tau in between 2 and 3, if I look at zk plus 1, it's roughly going to be zk to the power 1 over tau minus 2. And bear in mind, this is a number larger than 1. 2, for example. So then this says that the number of individuals in the next generation is basically a square of the number that I have now. That's extremely rapid growth. Okay? And that actually explains why you need so few generations in order to be quite large. And then actually you're going to grow extremely rapidly from that point onwards and even before that. So you need log n there, and you're going to be needing log n here. And basically before you're not going to have any connections between these two trees, and afterwards you're going to have tons of them. So the graph distances need to be the sum of these two, which in this case is going to give you 2 log n over the absolute value of log tau minus 2. And that explains the result in the main theorem. Now let me say something that goes a little bit in this direction for the configuration model itself. Because basically what this says is that the generation size one step from now is a power larger than 1 than the current generation size. That's what this says. There is a statement that you can also prove for the configuration model itself. It's not so difficult. And it basically says something like the following. So suppose we have a vertex satisfies that its degree is large, whatever that means. I'll just write it as k. Okay? Now you can ask the question, what is the highest degree vertex to which this vertex is connected? Right? So I have a vertex that has a humongous degree. All of these are going to be paired, of course, not in an independent way, really in the graph. And now I'm looking at the maximum degree vertex here. Yeah? How high does this grow? Okay. Well, you can show that the maximum over u in the neighborhood of v, so any of its neighbors, I know that there's k of them, of the degree of u is basically comparable to k to the power 1 over tau minus 2. So it's the same power growth as we see in the generations of the graph. And that you can actually use very quickly, not only to prove that the shortest path has the scaling of basically twice this number, but even in a very simple way of constructing an almost shortest path. So what you can do is you can grow your graph up to distance r, take the largest degree vertex in there. That's going to be of the order e to the power, a constant e to the power r, so it's very large. And then from that point on, you do precisely this. Every time from the point on, you look at its neighbor that has the highest degree. And then you look at the vertex neighboring that has the highest degree, and continue onwards. And this will tell you that this sequence of vertices will grow doubly exponentially, even in the graph. And that will actually produce a path that may not be the shortest path, but it certainly has the same order of magnitude as the graph distance. And that allows you to prove an upper bound of the form that the graph distance is at most twice this log n over the absolute value of log tau minus 2, which is a nice result. For a lower bound, you can do a first moment method, basically saying, if the graph distance is very small, then there has to be a path that is very short that actually connects to 2 points. Now, of course, you have to be very careful in these path counting techniques because you have infinite variance random variables. That is always tricky. So there's basically 2 scenarios. Either the degrees along your path grow the way as you expect them to grow, for example, something like this, or they grow more quickly. Okay? If they grow more quickly, you can give an easy bound that says that this is not going to happen. If they grow like this, then the path has to have length at least something like twice log n over the absolute value of log tau minus 2, and you're done. Well, this is a relatively simple first moment method. And path counting. Okay, I've tried to indicate sort of a little bit where these results come from. The very first time I read about this log n result, I was a bit surprised because it's so small. But here, I think this gives a very good intuitive picture where it comes from. And actually, these really are the ingredients of the proof. Any questions about this? All right. Now, one thing that I've also tried to explain last time and I wrote a theorem down, that was that if you do the same thing for the preferential attachment model, you get a result that is very much like this. It's just that the distances are twice as large. Okay? So let me write this down. If I look at Hn, which is now the distance in a preferential attachment model of size n, between a uniform starting point and a uniform ending point, then this is basically of the order 4 log n divided by log tau minus 2, where we should bear in mind that this power law exponent is 3 plus the delta over m, and these were the two parameters that we have in the preferential attachment model. The vertices come in with m edges, that's the m parameter, and they connect with probabilities that are proportional to the current degree plus a constant, and that's this delta. The constant is the delta. And here we're in the setting where tau is in between 2 and 3, so delta is negative. And it has to be larger than minus m, otherwise the model makes no sense. Okay? All right. So the whole crux here is this intuition. So let's think about this intuition for a preferential attachment model. Now, a vertex with high degree is typically one of the old vertices, relatively old vertices, because that still has a lot of time to accumulate a large degree. So if I have a vertex with a very large degree, I should really, in the preferential attachment model, think of it as being a very old vertex. Now, if I want to connect it to a vertex that has much larger degree, for example, its own degree raised to a power larger than 1, then this could, of course, occur because this vertex is connected in one go to a much older vertex. But this is quite rare. It's not going to do it. Okay? So the same proof for the configuration model is not going to be adaptable to the preferential attachment model. But what turns out to be the case is that if I have a vertex of very high degree, so this is a vertex for which the degree at time t is equal to k, which is very large, that's this one here, I'm not going to be connected in one go to a vertex that has this order of magnitude of a degree, but it will be connected in 2 steps to a vertex du of t, which has a degree which is of the order 1 over k to the power, this power larger than 1. Now, why is that? Well, you have very many choices for such a vertex, which I sometimes call an interconnector. And if you actually know in the graph that the graph obeys a power law, so you know roughly how many degrees there are of which order of magnitude. And then it turns out that because you have basically t choices for making this connection between such a vertex and these 2 of them, that the probability that something like this happens is very alike the probability here. But you really need this intermediate vertex. So that already says something about the difference in the topology between the preferential attachment model and a configuration model, when tau is in between 2 and 3. In the configuration model, sort of short paths go between vertices that have very high degree, but you really connect from a vertex which has high degree to a vertex which has much higher degree in one go. Whereas in the preferential attachment model, there seems to be some alternation. You have a vertex of high degree, it's connected to some vertex that probably has very low degree. Might even have degree m. But from that vertex on, you go to a vertex that again has this same order of magnitude as in the configuration model. And that's really the structure of shortest paths in the preferential attachment model. So rather than needing one step to go from a vertex of degree k to a vertex of degree k to the power 1 over tau minus 2, you need 2 steps to go there, which explains why the graph distances are twice as long. So rather than having 2 log n over log tau minus 2, you're going to get 4. And that turns out to be the real answer. All right. Any questions about this? Many of these things are very speculative, but many of them can also be made very much precise. Yes?
So you mentioned about preferential attachment.
Yes.
Are you requiring m to be bigger than 1?
Yes. Very good point. Yes, M has to be at least 2.
So then you're saying that whenever a node comes, then it will get connected to two very high degree nodes.
No, that's not what I'm saying. A typical vertex will come in and will connect to two vertices that have relatively low degree, because they're so plentiful. But every once in a while you do something strange, right? We actually know how the degree, for example, of the very first vertex grows. It grows with time. So it accumulates more degrees. So every once in a while there is a vertex late on in the game that will connect to it. And that will keep on happening. And it's the same here. If I have one of these vertices that has degree k, there will be a vertex somewhere along the line, 1, maybe 2 or 3. There's not going to be that many, depending on the precise order of magnitude you choose here. But there's going to be one that will actually do this. But it's a very rare one. It's not true for all the vertices. Typical vertices connect to vertices that don't have such a large degree. Does that answer your question?
Yeah, so maybe just a point.
Yeah. Absolutely not. No. So, very good point. M is at least 2. First of all, because you need these two edges to connect the 2 points. That's one. Secondly, because the result is false when M is 1. Because for M is 1, really the distances, I mean, you have a tree. And distances in such a tree are typically logarithmic. They can certainly not be smaller. And in fact, it's not very difficult to see that the height of the tree, if you root it at, let's say, the very first vertex, really is of the order log t, times a certain constant that depends on all the parameters. In this case, delta, and M is 1. So in a certain sense, M is 1 is not the interesting case. And you don't see this difference in phenomena for infinite variance degrees versus finite variance degrees. Good question. Any more questions? Okay.
So for the local convergence, you were taking R fixed, but
Yes.
when your coupling essentially was working because you say if I select uniformly a random one of these half edge,
Yeah.
probability that half edge is rating the structure of the structure.
Yeah.
This is more.
Yeah.
Will that work also for R that grows with that?
Yes. And in fact, it will work. It's easier to formulate it in terms of the number of vertices that you found. But it will work up to a size of the exploration tree which is of the order a positive power of n. When nu is finite, it's square root of n. When nu is infinite and tau is in between 2 and 3, it may be a little bit smaller, depending on what you require precisely of the coupling. Because your degrees are growing enormously, so you know, if I require that I don't see any self-loops in a certain generation, for example, then I have to let it grow up to a slightly smaller size. But I mean, you really see in the structure and the double exponential growth that if I am n to the power epsilon in a certain generation, then the branching process will be n to the power epsilon over tau minus 2 in the next generation, epsilon over tau minus 2 squared in the next generation, etc., etc. So you jump through these powers of n. Whereas here, it's much more slow. You really need an additional log n steps in order to go from n to the epsilon to n to the 2 epsilon. That's a big difference. Does that answer your question?
Yeah.
Very good.
Yes?
Yes?
I missed it, but until how long can you push this coupling between the brushing process in terms of n and
Small o square root of n when nu is finite. It's some very explicit power of n, I think n to the power tau minus 2 over tau minus 2 over tau minus 1 or something like that. But something pretty explicit for tau in between 2 and 3. But it changes a bit.
Anyway, it's always possible to get everything you want from just
Yes. Well, define anything you want.
anything you
All of the things that I've been describing, yes, that's enough. Yeah. Because somehow, already for the branching process, it's true that if you grow a large number of generations, when nu is finite, you get some law of large numbers effect kicking in. And you can show that that same law of large numbers effect kicks in the random graph in precisely the same way when nu is finite. Okay? So that's not so bad. For towing between 2 and 3, it's much more tricky. But somehow this statement is the same as this statement. This is in the random graph, and that's for the branching process. And we actually do know in this infinite variance setting that a positive proportion of the current generation comes actually from a single vertex. So it's actually not so bad. I mean, this is extreme value theory. If I have an infinite mean sequence of random variables, then actually the maximum will be of the same order of magnitude as the sum. Okay? So here I'm looking at one single instance. Here I'm looking at large sums. But there's not a big difference between them. But I mean, you really have to stop working precisely with the coupling and really you need to go to settings like this where you really look in the graph itself. Otherwise, you can't push it through so easily. All right. More questions? Okay. Okay. So far I've been talking about the configuration model. It turns out, and this is a very nice paper by Berger, Borks, Chase, and Saberi, that you can also do a local weak convergence statement for the preferential attachment model. But it becomes much more difficult. And it's much more difficult because the nice thing about this construction is that it immediately shows you that the branching process is highly homogeneous. There's a difference between the root offspring and the offspring of all of the other individuals. But apart from that, that's the only inhomogeneity that plays a role. Now, in the preferential attachment model, this cannot be the case, because somehow time enters into the picture, and you really have to take that into account. So here it's sort of a homogeneous branching process. If you want to do the same thing for the preferential attachment model, it will be a branching process, but it will be a multi-type branching process with lots of different types, in fact, a continuum of types, basically indicating the age of the individuals. But you can still describe this branching process and also show that the graph locally weakly converges to this, which is a very nice thing. And this is closely related to, in fact, a very nice property of a preferential attachment model that shows that you can describe it in a different way in terms of independent indicators. And this is related to Polya-Ernst schemes. Who knows about Polya-Ernst schemes? Who doesn't know about Polya-Ernst schemes? Okay. So a Polya-Ernst scheme is something very simple. You have a big vase. You know, probabilists are always thinking about balls and vases, right? So you have a big vase. You have colors. You have colored balls in them. A certain starting number of blue and red. You take a ball uniformly at random. You look at its color. Take another ball of the same color. Put it back. And then you can continue doing this experiment. Okay? It turns out that if you look at the proportion of balls of each of the two colors, that's a random variable. And it will converge as almost surely to a certain limiting random variable. And that's some sort of a beta distribution depending on the initial number of balls of each of the colors. But there is a very beautiful theorem by De Finetti about exchangeable random variables that will actually then tell you that if you look at the number of red balls at any given time, that I can describe this in terms of the limiting random variable. Namely, it will be the number of red balls at the starting point. Those, of course, are not going to vanish. But then in distribution, it's the same thing as a binomial random variable with a parameter n, because that's the number of draws that I do, and with a random success probability that is this limiting random variable. That's actually very cute, because I have a process that is highly non-independent. I mean, if I draw a lot of balls that are red in the beginning, I twist the probabilities towards red, and then also the proportion should be much larger. Okay? So there is a high amount of dependency on how you draw things. Still, you can couple it to an independent urn, so to speak, if you allow for a random parameter. Okay? Now, it turns out that if you look at relative proportions of vertices of the degrees of vertices inside a preferential attachment model, then this is actually very closely related to a Polya-Ern scheme. You have to be a bit careful. So if I look at the degree of vertex k and I divide by the sum of the degrees of all the vertices up to k, then this is like a Polya-Ern, but it doesn't change all the time. So if you inspect this at the times that you actually connect up to a vertex in between the first k vertices, then this is precisely a Polya-Ern scheme. So a relation like this is going to occur for it. And that actually allows you to describe the preferential attachment mechanism, which is fairly complicated, in terms of independent edges, or edges that are conditionally independent given a whole bunch of beta random variables. And that construction allows you to then push towards the limit. It's a beautiful construction. It's much more complicated than the configuration model. It's a very nice and beautiful construction. All right, so that was local weak convergence. Well, this was the first hour. Good guesstimate. So discussion of small worlds. I've been spending a lot of time trying to explain what graph distances in random graphs behave like, what the similarities are between the various models that we've seen. It was very obvious that the generalized random graph is very closely related to the configuration model because, you know, if you can do the appropriate conditioning, they have the same law. Preferential attachment model is completely different, yet in many respects, graph distances behave in a very similar way for the preferential attachment model as for the configuration model. So that's the kind of universality that I was talking about in one of my very first lectures. There are lots of random graph models, but you hope that at a somewhat higher level, they behave in a very similar way. Now, we've seen one example for which this is true. There's tons of other properties that are probably quite different, but this is at least a good setting. Now, one of the features that all of these models have in common is that they're locally tree-like. So locally tree-like means that if I look at a vertex, let's say uniformly at random, I draw one of the vertices out of the bag of all the vertices, and I look at its immediate neighborhood, let's say up to depth 10, it's very unlikely that I'm going to be seeing a cycle there. So there's very few triangles, there's very few cliques of size 4, cycles of length 5, etc., etc. You're bound not to see them. They may be there in the graph somewhere, and of course they are also involved in vertices, but the proportion of vertices that is involving cycles and so on is vanishing. Now we know that this is not true in the real world. We see typically many triangles in real-world networks. If only because, you know, if I have two friends, they might actually come to my birthday party and get to know one another, or we might go out together and they may actually get to know each other so well that they become friends themselves. Right? So there tends to be lots of clustering. And it's not at all clear whether all the properties that I've been describing so far persist to be true beyond the local tree-like setting. So for example, the fact that in all of these models, and somehow you have an infinite infinite mean branching process approximation, then you get log-log distances, well, it's not so obvious how that is going to be, whether that's still going to be true if you see lots of cliques. Because you may actually be wasting a lot of your degree in connecting to things that are already very highly connected, right? So this requires more thought. I do believe that there's universality at a somewhat higher level, but it's probably not going to be simply the degree distribution that you have to look at. You probably have to look at a bit more. All right. That's all I wanted to say about small world models. And after the break, I will tell you about smallest weight problems, rumor spread, epidemics, and competition processes.